So today we're going to talk about learning target 7, which is relating the domain of a function to its graph and to the quantitative relationship it describes. So to find the domain of a function, you first need to identify the independent variable, which means that we're talking about the x-axis and the x values. Remember that the independent variable is the x of the function. It is the input, or what you are able to control or change. So looking at this graph right here, these arrows on the end tell me that this graph goes forever to the right and forever to the left, which means that the domain of this function is all real numbers. In math, that's how we say it covers every number. We just say all real numbers. You have to say the real part because there's actually another set of numbers called imaginary numbers, but we're not going to talk about that in Algebra 1, so for now we will just say all real numbers. Over here, this graph starts at -4 and goes everywhere to the right. If you were to run your pencil like this along the graph, there's no graph, no graph, no graph, no graph, no graph, and at -4, bam, the graph starts. And then everything higher than -4, everything after -4, there is a graph going that way. So the domain is going to be all the x values that are bigger than or equal to -4. If you would rather not write it in the inequality notation, that's also okay. You could just say all x's bigger than or equal to -4. And that's okay also. Over here, this graph actually has an open circle right there on -3. So if we're going along, there's no graph, no graph, no graph, no graph. And then all of a sudden, here at -3, the graph sort of starts, but it doesn't start at -3. That's what that open circle means. It doesn't start there, but it starts just after. So we're going to say that it's all the x's that go from -3 up to, if I run my pencil along, this is a good way to just help me visualize where the graph actually is. From -3 all the way until I get to when x is 1, and then the graph stops. There's no more graph after that. So 1 over here, and because this is a closed dot and 1 is actually included, I'm going to put a line underneath because it's all the way up until also equaling 1. If I'd rather not write it with the inequalities, I can say after -3 until 1. That might be another way to say that. Okay? So that's graphs, but we're also talking about graphs. And this part right here that says the quantitative relationship it describes, that means situations. That's fancy words for situations. So we talked about the graph part, that's here. Now we're going to talk about the situations. Because a lot of times graphs really just represent situations. So if you're looking at a situation, the first thing you're going to do is you're going to identify the independent variable. Then you're going to ask yourself about various possible values that will or will not work or make sense for the independent variable. So let's look at this first example because a lot of times it's easier to understand something if we're just looking at examples. In this example, it says our situation is the height of a plant depends on how many ounces of water it gets. So in this situation, we give different plants different amounts of water, and then they grow to different heights based on how much water they're getting. I'm assuming the more water, the taller the plant. So in this situation, our independent variable is ounces of water. So to figure out the domain, all the possible things that the ounces of water could be, our independent variable could be, we are going to look at these 4 questions. Negative, fraction, 0, and a limit. If you consider those 4 areas of possibility, you're going to come out with a pretty reasonable domain for the function. So first, let's think about this first question. Is it possible to have negative ounces of water? No, you can't give a plant negative water. So right now. Is it possible to give a plant fractions of ounces of water? Like, could you give it 3.5 ounces? Yes. Is it possible to give a plant 0 ounces of water? So no water at all. Yes, that's possible not to water it. Is there a limit to how much water a plant can receive? Theoretically, no. You could just keep pouring water on that plant all day. So a reasonable domain for this function, it can't be negative, it can be a fraction, it can be 0, but there's no upper limit. So any number, fraction or not, 0 or bigger. So that's what we can write. We can write any amount, 0 or bigger. That's one way to describe the domain of this function. Now let's look at the second one. How many people on a bus determines how long the bus ride is? There is a maximum of 45 people on the bus. The independent variable is people on the bus. Our negative, now I made a mistake because I just copied and pasted. This should say people. Fractions should also be people. 0 ounces of water should also say people. Is there a limit to how many people can be on the bus? Okay, so we'll change all these ounces of waters to people here. And then this last one, we kind of have to rewrite a little. So that's what this should say. Sorry about that. So if we're thinking about people on the bus, are negative people reasonable for this situation? No, we can't have negative people. Are fractions of people reasonable? Nope, we're not going to cut anybody in half. Is it possible to have 0 people on the bus? Yes. There can be nobody on the bus. Is there a limit to how many people can be on the bus? Yes. 45, right? Because it says there is a maximum of 45 people on the bus. So a reasonable domain for this function is, we can say all whole numbers from 0 to 45. And just to clarify, whole numbers is a way to say not fractions. Okay? And that is what we need to know about the domain.